In the previous lecture, we talked about reinforcement learning related to the V function. That was the if you had a given policy, didn't know whether it's optimal or not. If you follow that policy, you can calculate the V function that gives you the discounted reward for each state, starting in that state and then following that policy. The downside to that is that you have to try all different policies, all different pi functions, evaluate the V functions for all of those, and then pick the policy that looks like it's optimal based on all those calculated V functions. Today we're going to talk about Q learning, or a Q function that eventually is going to allow us, just by exploring the environment, to learn a Q function, which is a reward function. And it's going to tell us that if we're in a state S, we can look at all possible actions out of that state S, look at the Q function, and then find a that's maximal. So this Q function is going to depend upon not just the state that we're in, which is what the V function does, but it also depends upon what different actions we can take out of that state. So if you're in state S, then you look at all different possible actions, and then you pick the one that gives you the maximal Q function, the Q value, and that tells you that that's the best way to go. So in this part one of the Q learning lecture, we're simply going to learn how to calculate Q functions. We're not going to learn them. So we'll be given a V function or a policy, and then we'll calculate Q's, and then in the next lecture I'll show you how we actually learn from experience. Alright, so the first thing we need to recall is that the V function, if you remember, for a given policy pi, and we're in a state Si, the way we calculated that last time with our example is you are in state Si, you take an action Ai that's given by the policy pi, because pi tells you what to do when you're in this state. So you collect the reward for doing that action out of this state, and then you get into the next state and you keep following the policy pi forward and collect the rewards going forward till you get to the goal, and you discount those. In the example we saw that you can calculate the V function for a given state and policy pi by the immediate reward plus the discount rate, and then the V function for the next state you end up in. So you could step forward one state following policy pi, and if you know the V function there, then you're done calculating. And that's why when we did that example, we worked our way backward, outward from the goal. So let's talk about if pi is the optimal policy pi star. If that's true, then the V function for that is calculated according to the formula above. You follow the optimal policy pi star, you collect the reward following this policy, and then you look at the V function at the next state and you add that in discounted by gamma. So this is saying, well, we only allow the optimal action based on the policy. But what if we said, okay, let's take any step going out of state Si. Can we calculate pi star based on that, or V pi star? Well, sure we can. We simply try all possible actions A going out of state Si, and then we evaluate R plus the optimal V for the next state, and then we maximize over that. Makes sense, right? So if we want the optimal V, we try all possible actions. We take that action, and then from then on, we follow the optimal policy. So if we can do that, then we can calculate the V for the optimal policy for our current state. Still have an issue here because we have to know the optimal policy going forward from the next state, but at least this gets us one step closer to going where we want to go. And if we can do that, then we can get the optimal policy, again, by just searching all possible actions out of the state and then we search over the reward plus the discounted reward following the optimal policy. So that's going to give us the optimal way to go out of state SI if we know the optimal policy for the next state. And so if we can learn V pi star, we're done. So if there's some way we can learn this, we're good. The only downside to that is, implied in here is that we're going to need to know where, if we're sitting at state SI and we try an action, where we end up. That maybe seem obvious, but if you have an agent like a robot in a room and you simply take an action, we may not know a really good model of where the robot's going to end up at the next state. This delta function implies that we can predict if we take an action A and we're in this state, this is where we're going to end up at the next state, SI plus 1. That means we have a system model, which is not always true. We want this thing to work for a robot exploring an unknown environment, and it simply goes to a new spot. So that's what this is saying down here, is that we're going to need a system model. We don't always have. We will have a reward function, but the reward function may not come until after it ends up in the next state. So the way to get around dealing with all these V functions and optimal policies is that we're going to use a Q function that circumvents needing to know what the next state is. So the idea here is that if we somehow can calculate a Q function, we don't need to be able to predict where the robot will be in the next step. So we're going to define Q to be this quantity up here in brackets in this formula. It's going to be this whole thing here. So for any action A, Q is going to collect the local reward, and then it's going to collect the discounted reward, assuming we have known some optimal policy. So that's the definition here. Q is defined to be, if you're in state S and you take action A, you collect the reward, and then you collect the discounted reward for that next state. So again, we're going to need to know the V function for the next state to calculate this. But then once we learn how to learn Q, then we won't need that even. So again, what this says is, if you're at state S and you take action A, Q is the immediate reward plus the discounted cumulative reward following the optimal policy from then on. So again, it's like before, if we take one step and then we're assuming that after we take one step, we can kind of follow an optimal policy going further on. At least we're one step further toward the goal in an optimal way. The nice thing is, if you know your Q function, then you simply try all possible actions out of that state, pick the Q that gives you the most reward, and then that becomes your optimal policy. So this is key, because it says if we know Q, then we can find the optimal policy, which I just stated this here. We don't need to know the reward as a function. We simply collect the reward from the environment, and we don't even need to know a system model. We simply move, and then we sense what state we're in at the next state. All right, so we're going to go back to our example, the grid world that we had before, and we're going to evaluate the Q function for one of the policies that we used last time, pi 2, that was optimal. So I'm going to grab the results from the previous example, and let me highlight these in green. So in the boxes are the V functions that we calculated last lecture for each of the states. And we did that with the policy pi2. And in fact, we used these v functions and we said, this looks like a good policy because the numbers in the boxes were bigger than that initial pi1 policy that had a lower value in a couple of the boxes. So key here is, in this drawing, the box is the v function for following policy pi2. And pi2 we saw is an optimal policy. In the arrows here are the reward functions that we had defined already before. So this is a reward for going from 2 to 4. This is the reward for going back, and so on. And remember, the only actual non-zero rewards are the 100 values for going into the goal. Everything else is 0. We're going to need to know these rewards because we're going to calculate this Q formula. We need to know the reward, and we need to know the V in the next state. The next picture that I have drawn here is that we've got to come up with a notation for keeping track of where we go from what state to what. So I'm going to define A12 as the action starting in 1 and going to 2. So here's A24, here's A42, A12, A21. So A12 goes from 1 to 2, this goes from 2 to 1, A56 goes from 5 to 6. Just a notation to keep track of what actions are what. So now we're going to calculate the Q values for each action at each state. So for each one of these arrows here, we're going to get a Q value. And we're going to use the optimal policy pi2. So remember what the formula is. Q for being in state S, following action A, you collect your immediate reward. So that's going to come from the rewards up here. And then you take gamma, and then we're going to look at grabbing the V pi2, which is the number in the green boxes up here. So for example, if we go from 2 to 4, so we're in 2 and we go to 4, we're going to collect this reward, and then we're going to use the V value for the next state here. And we're going to do that for each possible action. All right, so the way I organize this is these are the states, or sorry, these are the actions that go out of state 1. So we're in state 1, and there's two different ways we can go. We can either go from 1 to 2, or we can go from 1 to 3. Again, go back up and look at the picture. If you're in state 1, you can go up to 2, or you can go over to 3. So we have to calculate a Q for each one of those actions. So going from 1 to 2, we collect the reward, which is 0, plus gamma times the V for the next state that we end up in. So we collect a 0, and then the V for the next state. So we went from 1 to 2, jump back up here. The V function for state 2 is 90. So that's the V. We went from 1 to 2, collected 0 reward, and then 90 is the V function in that square. Same thing for going from 1 to 3. We collect the immediate reward, and then the V function for state 3. Go back up here. Here's state 3. Its V function is 90. So once we get the hang of this, then we've done the Q values for going from 1 to 2 and 1 to 3, and we've written those down here. So there's the Q going from 1 to 2, there's the Q going from 1 to 3. So now we go to state 2 and we say, okay, we can go either from 2 to 1 or from 2 to 4. So we have to calculate those Q values, and that's done up here. So if we're in state 2, we can go from 2 to 1, which means we collect the reward of 0, and then we grab the v function for the state, the next state, which is 1, multiply by 0.9, and we get 72. So we write that down here. So that's the q going from 2 to 1. And then we go from 2 to 4. So we collect the reward of 0, 0.9, and then what's the v function for state 4? We have to go back up here. State 4 has a v function of 100. Remember, that was pre-calculated from the previous example last lecture. So this turned out to be 90, and we write that in here. All right, so the next thing we're going to do is look at all the possible ways we can go out of state 3. So we're in state 3 here. We can go up, over, and over. So we have to calculate 3 different q's. Go from 3 to 1, 3 to 4, 3 to 5. So the calculation is the immediate reward from going from 3 to 1. And then when you're in 1, the v value from up above is 81 right here. Stick that in and we get 72. And so we write that in right here. I think you get the idea, so we can go through the rest of these rather quickly. If we go from 3 to 4, collect the reward. We're in 4. The v value for 4 from up above is 100, so we get 90, and we write that in here. And then we go from 3 to 5, collect the local reward. When you're in 5, what's the v value for 5? Let's go up and look. Being in 5, the v value pre-calculated is 100. So we get 90. And we write that in right there. So we're left with being in state 4. You can go this way, or that way. So we do those 3. Same process. Local reward. Look at the v for the next state. We get 81. Write it in here. Write it in here, and write it in here. Always take the local reward, and then once you get in the next state, write the v value. And then finally we wrap up with 5. There's 2 ways you can go. You can either go up this way, or you can go over this way. So from 5 to 6, we collect a really big prize of 100 local reward. Once you get into 6, it's 0, and so the q value is 100 for that one. And notice the same thing happened up here, is that this is the only time that we had a good local reward, and then once you get into 6, the v value there is 0, so all you get is the local reward. All right, so now we look at this diagram here, and for any state, we can figure out, well, where's the best thing to do. So let's say we're in state 2. There's 2 options. We can go this way, or we can go this way. The q for going down is 72. The q for going over is 90. So it's real clear that going over and collecting 90 is the best. How about state 5? You can go up with a q of 100, or you can go over with a q of 81. Obviously the best way to go is up. So once you know the q value for each state and each action, it's real easy to say, okay, if I'm in state 1, I know exactly which way is to go to get optimal. But you say, well, we needed to know the optimal policy to calculate those q values. Yeah, we did. But the advantage of the q is in the next lecture, we're going to learn that even if we don't know an optimal policy, we just explore the environment and we can learn this q function, and then it will tell us which way to go optimally. So we can learn q just from the environment, and that completes the picture of how you can learn an optimal policy without actually knowing anything about the environment at all. So this is just a diagram that shows the different optimal paths that you can take. if we're in state 1. So following the Q values, the path of highest Q values going out of 1, it doesn't matter whether you go up or over because the Q value is 81. Once you get into state 2, it's obvious that you need to go over. And once you get into state 4, it's obvious you need to go over and collect the 100. If you decided to go this way, once you're in 3, you can either go up or over. The Q values are the same. But then once you get over here, you obviously want to go up. And when you're in 4, you want to go over because the Q values going the other directions are less. All right, so that's the end of part 1 here. The next thing we'll do next time is an algorithm for learning Q, and I want to take a break because, as you can see, the theory behind it is a little dense, and so we need to rest before we do that.